Welcome to the listening section of the TOEFL mock test, brought to you by Spinta. This section measures your ability to understand conversations and lectures in English. In this section, you will listen to several conversations and academic lectures. Each conversation and lecture is followed by a number of questions. You will hear each conversation or lecture only one time. You may take notes while you listen. You may use your notes to help you answer the questions. Some of the questions will replay part of the audio for you. Answer the questions based on what is stated or implied by the speakers. You must answer each question before moving on. You cannot return to previous questions in this section.
Good morning. Today I want to discuss climate feedbacks and tipping points and why they matter for both climate science and policy. Feedbacks are processes that can amplify or dampen the initial effects of warming. Tipping points are thresholds beyond which a system shifts to a new state and may not return to its previous condition. Both concepts are central to understanding long-term climate risk. We will start with concrete examples. The ice albedo feedback is a classic positive feedback. As sea ice melts, it exposes darker ocean water, which absorbs more solar radiation, which in turn accelerates warming and leads to more melting. This mechanism contributes to what we call Arctic amplification, where the high latitudes warm faster than the global average. Another important positive feedback arises from permafrost. Permafrost soils hold large amounts of organic carbon. When permafrost thaws, it exposes that carbon to microbial decomposition, which releases carbon dioxide and methane. That additional greenhouse gas enhances warming and can cause more thawing. This links physical warming with a biological source of emissions. Water vapor is also a positive feedback. Warm air can hold more moisture. Since water vapor is itself a greenhouse gas, warming leads to more water vapor and further warming. Cloud feedbacks are more complex. Depending on altitude and type, clouds can either cool by reflecting sunlight or warm by trapping infrared radiation. Many climate models show a net positive cloud feedback, but there is still uncertainty in the magnitude and even the sign in some regions. Now consider large-scale systems that could tip. Examples include collapse of the Greenland ice sheet, shutdown or slowdown of the Atlantic meridional overturning circulation, and dieback of the Amazon rainforest. These are not just academic concerns. For instance, the Greenland ice sheet contains enough ice to raise sea levels by several meters over long timescales. If a threshold is crossed, communities on low-lying coasts would face irreversible changes. Tipping points can exhibit hysteresis. That means the path to the new state is not easily reversed by simply reducing the forcing to its original value. For example, if an ecosystem loses key species or soil quality declines, recovery may require conditions that are much more favorable than those present before the collapse. Modeling feedbacks and tipping behavior is challenging. Many global climate models capture physical feedbacks like water vapor and ice albedo, but they often simplify biological and chemical feedbacks, such as permafrost carbon release or methane thaw. That simplification can lead to underestimates of long-term warming in scenarios that push the system toward thresholds. There are empirical case studies that illustrate these dynamics. Observations in the Arctic show accelerated sea ice loss and increased permafrost thaw. In the Amazon, a combination of drought and logging has moved parts of the system toward a state where savanna replaces rainforest. These examples show how local stressors can interact with global warming to move systems closer to tipping points. From a risk management perspective, we need to think about early warning indicators. One such indicator is increased variance or autocorrelation in system behavior. When a system approaches a threshold, it may take longer to recover from perturbations. This phenomenon is called critical slowing down, and it can be detected statistically in some observational records. When I mention critical slowing down, I mean that recovery from perturbations becomes progressively slower as a system nears a tipping point. Detecting these signals in the real world is difficult because climate systems are noisy and observations are limited in time. Still, looking for changes in variance and autocorrelation can provide useful clues. Policy-wise, this argues for precautionary approaches. Because tipping points involve potentially irreversible outcomes, avoiding trajectories that bring us close to thresholds is prudent. To conclude, feedbacks and tipping points add nonlinearity to climate change. They increase uncertainty and risk because small changes in forcing may produce large changes in outcomes. Effective responses combine mitigation to reduce greenhouse gas emissions and adaptation strategies that increase resilience. Understanding and communicating these processes is essential for informed decision-making.
Listen again to part of a lecture, then answer the question.
When I mention critical slowing down, I mean that recovery from perturbations becomes progressively slower as a system nears a tipping point.
For more TOEFL mock tests, as well as IELTS and Cambridge practice, visit www.spinta.org. We provide updated tests every single day, AI feedback for your speaking and writing responses, and access to a wide range of high-quality mock tests to help you prepare with confidence.